We're getting into chapter 5 now, which is on friction. Something about a replacement hip here. Yeah, another overproduced video. You can skip. Okay, so friction is a force that opposes relative motion between surfaces in contact. And there's two main kinds, kinetic friction and static friction, and they're very different the way you treat them in physics problems. So it's important to distinguish them. Kinetic friction is if two surfaces are in contact and are moving relative to one another. Then you call that kinetic friction. And one of the ways I remember kinetic friction is that it generates heat. If you take your two hands and rub them together, you can feel that heat that's generated. That's one of the properties of kinetic friction. It's dissipative in that it converts the energy of motion into heat, which is sort of lost from your system. So like if a crate is sliding along, the reason for the kinetic friction is that the bottom of the crate isn't actually a rough surface, and even the floor is a rough surface. If even the smoothest crate and the smoothest floor, if you were to look under a microscope, you would see hills and valleys, or stalactites and stalagmites, and they would bump into each other as it moves. And this is the okay, so and this is the equation. So it turns out, so you would think that it would be very complicated to actually figure out what friction is, because what's going on depends on the shape of these two surfaces. But miraculously, and I think sort of surprisingly, it turns out you can model friction with an approximate equation. And it's the friction is equal to, this is the Greek letter mu, so it sort of looks like a little u or something, and it's got a sub k because k stands for kinetic, so mu sub k, that's a dimensionless constant, times n, where n is the normal force. So you may think that the normal force has nothing to do with it, but I think the more two surfaces are pressed together, the more friction you get, and there's this, I guess, linear relationship is what it's saying here between the amount of normal force and the amount of kinetic friction that you get. So it's a model. It is an empirical model because it was just, people came up with it based on experiments. There's no theory behind why this should be the kinetic friction. It just turns out that it's an equation which works pretty well. Discovered by Coulomb long ago, and we're still using it. Engineers use it, and it seems to work pretty well. So we know what normal force is. What's the mu sub k? Well, what it is a dimensionless constant which depends on the kind of surface. So in this table 5.1, they give you a bunch of examples of coefficients of kinetic friction. So example, if it's rubber sliding along dry concrete, then the coefficient of kinetic friction is 0.7. Meaning to find the friction, you take 0.7 and multiply it by the normal force between those two surfaces, and etc. It's always dimensionless. There's no units to the coefficient of kinetic friction. It can be really low, like Teflon on steel, that's something really slippery, or it could be really high. Shoes on wood, that's purposefully made really high, 0.7, so that it's comes to a stop when it's sliding a lot quicker. Okay, so going back, now there's the other kind of friction called static friction. This is very different. Static friction occurs when the two surfaces are not sliding. They're kind of locked together, and basically it just keeps them locked together. And it can have any value. This is a very weird thing. It looks like an equation, but it's not an equation. It's called an inequality. It means that it's less than or equal to mu sub s times n. So it looks a little similar. You've got this coefficient of static friction from table 5.1, and you've got the normal force, but really the static friction can be anything. So it can be 0 if there's no reason for the two surfaces to slide, or it can be up to this maximum value on the right here. But it's a self-adjusting force, kind of like the normal force or tension, and so there's really no equation for it. There's just this equation for the maximum. So you can take a look at these coefficients of static friction. What's interesting is that they're always a bit higher. Once something, I guess, stops sliding and kind of locks in, then the maximum force that it takes to get it sliding is a bit bigger than the force of friction as it's sliding. But yeah, what these will give you, if you multiply these numbers times the normal force, then you get the maximum static friction force before it starts to kind of breaks and starts sliding. And there's a little take-home experiment. Again, these x-rays, which are pretty random. This is the kind of question that you're going to get, is that you draw a free body diagram, you've got a normal force, which you have to find, right? Because you have to balance forces in this perpendicular direction. They put this little symbol is perpendicular and this symbol is parallel. So sometimes I make this the x direction and the y direction. And then you've got the friction, which is in the parallel to the surface direction, and the normal, which is in the perpendicular. And then gravity, the weight here, is the diagonal force in this case. So I would definitely go through that example, make sure you can solve these kinds of problems. And here they're giving you an explanation. Smaller normal force, you'll have a less friction. They're less locked together. Larger normal force, they're more locked together. And the next section is about what's called drag force. I've been calling this air resistance. So basically, I think what I told you before is that when something's moving through the air, there is this force of air resistance which opposes this velocity. But air is a fluid, and so this is a problem in fluid dynamics, and it's quite difficult to solve. But kind of like friction, there are models for this air resistance. And one of the models is that for most large objects, like bicyclists, cars, and baseballs, not moving too slowly, the magnitude of the drag force it's opposite to the velocity, but it's proportional to the speed squared. And you get this equation, 1/2 c rho a v squared. That's the Greek letter rho, where c is a dimensionless drag coefficient. A is the area of the object facing the fluid, so I call that the cross-sectional area. So if it's going cross-sectional, means if its velocity is going one way, then perpendicular to the velocity is there's a kind of area. And rho is the density of the fluid, so the density of the air or something in kilograms per meters cubed. There's not much you can really do with this equation, but you can calculate terminal velocity. There's some different drag coefficients, dimensionless drag coefficients for different shapes, and I guess surface properties, how slippery it is or something. Okay, yeah, so this is the real equation. If something is falling, then as it's speeding up, if it's just falling straight down, the speed gets bigger and bigger, and so the drag force gets bigger and bigger. And if you take the net force in the downward direction, it's mg, so I've defined positive as being down. Mg is positive gravity minus the drag force, which is up. And that'll give the acceleration. Well, it'll stop accelerating when these two are equal, and you get a zero net force. So if you set the gravity equal to the drag force, you get what's called the terminal velocity, or it's terminal speed really. It's the magnitude of 2 times mg divided by rho ca. So you can figure out what's the fastest that something will fall before the air resistance equals the gravity, and it just falls at a constant speed. Turns out to be, for a skydiver, for example, about 98 meters per second. So you don't just keep going in free fall if you're a skydiver. It turns out that even after around 10 seconds, you're going at constant speed because there's so much air resistance. You're basically lying on a bed of air, and you kind of feel that weight again. Okay, so that's really the only thing you can do. And then there's another equation for drag force that's dependent on v. So this is when the object is very small or going slow, or is in a sorry, that's my neighbor's dog. There's a squirrel. Or is in a denser medium than air. So this is Stokes' law. Like if you're going through honey or something like that, then the drag force is proportional to speed. This section, 5.3, is about elasticity, stress and strain. So this is about another force called, I call it the elastic force, okay? And it is due to these little deformations. So if I take, for example, this eraser and I, squish it with a force, well, then the eraser presses back. And also it's squished, so it has some length L, Well, it has a little change in length, delta L, a tiny little delta L change. So if you look at this equation, it's something called Hooke's law. It was first written down by James Hooke, which says that there's a proportionality. The force is proportional to how much this length changes. F equals delta L multiplied by they just call it a proportionality constant. Now this one, unlike the coefficient of friction, this one has units. It has units of force per newtons per meter. So you multiply by a delta L in meters, and you get a force in newtons. Another way of rearranging that is to say, this is again called Hooke's law, the delta L is equal to F over K. So if you were to plot on this graph, delta L versus F, you get these different regions. There's the proportionality region. The Hooke's law is obeys for small delta L's. The slope of this straight region is 1 over K, where K is that proportionality constant. And then usually if you overstretch something or overcompress it, then it fails. It starts to fail. Then it deforms, and eventually it actually breaks. Figure 5.12 is showing you how the same force can produce different delta L's for different guitar strings. Same material but thicker, or a different material. There's something called the elastic modulus. Here is also called the Young's modulus. It has a letter symbol Y. And here's another formulation of Hooke's law. Delta L is 1 over Y times F over A L sub 0. So different materials have different Young's modulus value. And then when you make a long rod or cable out of that material, then you can use this more general equation to find how much it stretches. And it's not just proportional to the Young's modulus, but also the cross-sectional area, which is what A is, and also the length. The longer the length, the more it's going to stretch. And if you keep going down, you'll find that there is something called stress and strain. So the idea here, the concept, is that when you stress something, there's an external stress, then that object experiences strain. And so here the force divided by cross-sectional area is what's defined as being stress. And then the strain is defined as the change in length divided by its full length. So the fractional change in length is proportional to the pressure, the force divided by area. And that's proportionality is the Young's modulus. And now you can really see that it's the same as Hooke's law. It's just that proportionality constant is the Young's modulus times A over L like the original length. So stress is always a ratio of force to area. Stress has units of newtons per meter squared, also called a Pascal. And strain is a dimensionless change in something's length or size. And so stress is some Young's modulus times strain. Now it's also possible to stress something sort of sideways or perpendicular to its length. And that's called a shearing force. So there's shear stress. And the shear deformation equation is that sideways distance delta x is 1 over s times the stress times the length. So S here is called the shear modulus. And if you go back up to table 5.3, you'll see shear modulus for different materials as well. So for example, you can find how much a nail might bend if something was hanging, a weight was hanging off of it. And lastly, there's something called bulk modulus. So it's the last column in table 5.1. And this is this idea that if something is inside a pressurized fluid, it can actually decrease its volume a little bit, even a solid will. So, and delta V is proportional to 1 over the bulk modulus times that pressure, external pressure, times its original volume. And water, for example, has a bulk modulus. So down at the bottom of the ocean, water actually is compressed. It's a little more dense than it is, and that's because of this enormous pressure at the bottom of the ocean. So even though the bulk modulus is 2.2 times 10 to the 9 newtons per meter squared, since the pressure is so high, 5 times 10 to the 7, you actually get a 2% decrease in the volume of water when it's 5 kilometers below the surface of the ocean. And that's it for chapter 5. Bye for now.